and we got into it last time, I believe. So we talked about obviously some important units, and really for our class and most chemistry classes that you take, kind of three important units is atmospheres, which is 1 atm, and that equals 760 torr, which is another very common unit of pressure, and that equals 760 millimeters of mercury. A reminder that 1 torr is equal to 1 millimeter of mercury, so it's a 1-to-1 conversion. So basically, you need to convert things between those two. You simply just change the units. It should be the same number. 760 obviously is an important number between these three units. And again, if you have atmospheres and you want torr or mercury, millimeters of mercury, you would multiply by the 760. The atmospheres would cancel, giving you a torr or a millimeter of mercury. If you have torr or millimeters of mercury and you wanted atmospheres, you would divide by the 760 to do that correctly, and that will get you atmospheres. We talked about some gas laws. We talked about Boyle's law, which is our P1V1 is equal to P2V2. This is at constant temperature here. And the pressure and volume can really be any unit you want, as long as they are the same on both sides of the equation. The sort of what we saw here was as the volume goes up, the pressure goes down, and vice versa. As the volume goes down, the pressure will go up. So basically, as the volume is shrunk, the gas molecules are in a much smaller area, going to cause more collisions to occur, and we would see a rise in the pressure, as opposed to the opposite. If the volume increases, gives everybody a lot more room to fly around in. It's going to take longer for collisions to occur, and we'll start to see the pressure start to drop in that situation. We also talked about Charles' law and Guy-Lussac's law. That's V1T1 is equal to V2T2. And also Guy-Lussac's, which is, by the way, this is at constant pressure. And P1T1 is equal to P2T2. That is at constant volume. And that's Guy-Lussac's law. And what we saw here was taking sort of the constant volume into account first. As the temperature increases, we would see an increase in pressure. And that is because as the temperature increases, the gas molecules should be flying around a lot faster, which means the volume is fixed. So they're going to hit the container a lot more often, going to cause a lot more pressure, and we will see pressure start to increase in that case. If we lower the temperature, the pressure will start to come down. Same reason, if we lower the temperature, basically our gas molecules will be flying around slower, and the volume is not going to move at all. So they have the same amount of space to fly in. That's going to cause collisions to start to come down, and we would see a decrease in the pressure as a result of that. Now, with Charles' law, because it's able to maintain constant pressure, what we see is when we do increase the temperature, like we talked about a second ago, we would see our gas molecules fly faster. But in this particular case, what happens is the volume will also increase as well. So the volume will go up. And the purpose of the volume going up in this case is because our gas molecules are flying around faster. They need a lot more room to fly around in to maintain the same number of collisions. And because they're able to do that, that means that we do have a constant pressure that will occur in that case. And vice versa, if we lower the temperature, the volume will actually lower with it. And again, here, if we lowered our temperature, gas molecules flying slower, which means we kind of need to squish them together in a smaller volume to maintain the right number of collisions and also maintain the pressure in that case. So in Charles' law situation, the way it's able, again, to maintain pressure or keep it constant is actually the volume will adjust accordingly based on what happens with the temperature. And again, in sort of Guy-Lussac's law there, we do not get that volume adjustment. So we do see the actual increasing or decreasing with pressure because we have a constant rigid sort of volume. The other really important thing with these couple of gas laws and pretty much all gas laws is the relationship we saw with Charles' law is if you graph volume versus temperature, no matter what gas you're doing, if you bring it back to sort of the temperature line there, if you draw your line all the way down there, it always hits that minus 273.15 number, which basically means pretty much every single gas law we do need to convert to Kelvin. So we got to add a 273 to that. So it is, as I said before, a no-brainer situation. If you are using any type of gas law, you got to have it in Kelvin. Again, even if you are given it in Celsius, you want the answer in Celsius, you have to put it in Kelvin to put it into the gas law, and then do conversions afterwards. We then talked about, I think, our friend Avogadro, he had a little law action, I think. And Avogadro's law dealt with moles, which is V1 over N1 is equal to V2 over N2. This was actually at two types of things here, constant temperature and pressure. So under a kind of constant temperature and pressure situation, what we do see is the volume and the number of moles are basically related to each other. So if you have like one volume, you got 1 mole, you got 2 moles, you got 2 volumes. So they're sort of proportional to each other. Kind of taking all these equations together, we get the ideal gas law, which I think is sort of where we finished up on last time. And that is PV is equal to nRT. This gas law here is different than all the others. It obviously is just a one situation. You got one pressure, one temperature, one volume. It also is the most restrictive in terms of units. When you use this, the pressure does have to be in atmospheres. The volume has to be in liters, the moles has to be in moles, and the temperature has to be in Kelvin. And that's really because R is a gas constant, which is 0.08206, and it has units of liters times atmosphere divided by Kelvin times mole. So because this is a value that you always have, not always given to you, but you always have that value to use, it does have all those units. So in order for everything to properly cancel out, whenever you use the ideal gas law, those are the units that everybody has to be in. The good thing is, if you just remember these units that go with the gas constant, it pretty much tells you what units everybody else has to be in when you use it in the gas law. We also talked about as well, one little spot right there, STP. STP is standard temperature and pressure. And remember that it does represent actually a pressure and temperature value. The temperature here is 273 Kelvin, and the pressure is 1 atmosphere. So if you are at that temperature and that pressure, that is what is referred to as being under STP conditions. There is a conversion factor that you could use when you are at STP conditions, and that is 1 mole is equal to 22.414 liters. A reminder that this conversion factor can only be used if you are at STP conditions. So if you are not at STP conditions, you should not use that sort of conversion factor. You should use the ideal gas law. If you're not sure you should use that conversion factor at all, you can use the ideal gas law for any conditions, STP conditions, non-STP conditions, whatever conditions you want. You can always throw all the numbers into the ideal gas law and always use it, and you don't have to worry about, that conversion or anything like that. Obviously, if you did, the temperature would be 273 and the pressure would be 1 atmosphere when you would put it into the ideal gas law if you chose to do that. Any questions on any of that stuff there? I think we talked about last time. Okay, so I think we left off with an example that I don't think we did not do this one, right? So let us start with this one. Calculate the pressure 1.82 moles SF6 gas in a steel vessel at 5.43 liters and 69.5 degrees Celsius. So take a couple minutes. Okay, let's take a look. So again, as we talked about last time, it's a good idea just to pull out the information from the question. So we're looking for a pressure. We do have moles, which is 1.82. We do have a volume that is 5.43, and we do have a temperature that is 69.5 degrees Celsius. So just looking at that, you could clearly get rid of all the gas laws that we used before, since we don't have any pressures. 2 of them are 2 volumes or any of those things. And it really should point you in the direction of the ideal gas law here. You can almost kind of see it there. A reminder that although not usually given to you in any problem, you always have the value of R available to you, and that is, again, a number you should know. And so that's just something that you always have. So in this case, we're looking for pressure. We do have the volume. We do have the moles given to us, R and T. We just want to check units here. So our volumes in liters. And like normal here, our temperature is not in Kelvin, so we do need to do a conversion. So that's going to get us a T73 plus a 69.5, 342.5 in this case. And that means that PV is equal to nRT. We're going to take volume to the other side by dividing it over there. And that would give us P is equal to nRT divided by V. Putting in our values here for N would be 1.82 moles. Our R, which again, you can use the rounded version to 0.0821 if you like as well. And our temperature in Kelvin, all divided by our volume here in liters. In terms of units, the liters on the bottom and top cancel, Kelvin and Kelvin cancel, moles and moles cancel, leaves us just atmospheres left over, which is good because we're solving for a pressure in this particular case. 1.82 times 0.08206 times a 342.5 and divided by a 543, looks like a 9.42 atmospheres here. Any questions on that calculation? Now, a couple of variation very commonly. In this case, we were given everybody in moles, but it's very common that you do have to do the grams to mole conversion using the molar mass in these type of problems. Also, obviously, our temperature, the Celsius to Kelvin conversion, and the other all common conversions actually with volume, very common. Like you collected your gas in lab. You collect it a lot of times in milliliters, so milliliters to liters is a constant sort of a very common conversion that you need to do when you're doing the ideal gas law. So a reminder, 1,000 milliliters, right, equals 1 liter, right? So those three sort of conversions are very common ones that you have to do when you're kind of doing ideal gas law. Any questions on that there? Okay. So let's talk about another gas law here, one that actually takes into account all the three variables, both pressure, volume, and temperature all together. We actually take the ideal gas law and solve it for R in two different situations. Since R is a constant, we could set these guys equal to each other, and we get this relationship here of P1 V1 over N1 T1 is equal to P2 V2 N2 T2. In most cases, the moles pretty much stay the same, as long as you don't open the top. And what that leaves us is what is sometimes referred to as the combined gas law. And that is P1 V1 over T1 is equal to P2 V2 over T2. Once again here, pressure and volume can be any unit you want as long as they are the same on both sides. And like normal here, though, our temperature obviously needs to be in Kelvin. So this is the combined gas law, and just take a moment here to talk about the combined gas law and all the other gas laws that we've talked about up until this point. If I had to choose to remember two gas laws, perhaps I would choose to remember the ideal gas law, PV equals nRT, and I would actually choose to remember the combined gas law. Actually, I might even choose to remember it in this version here, which is P1 V1 N1 T1 is equal to P2 V2 N2 T2. Why, if I was to invest the time, I would just invest on those two. Really, the reason is if you look at the combined gas law, you pretty much can, if we rewrite it sort of in that form, P1 V1 N1 T1 P2 V2 N1 T2 T2. So pretty much if you remember this one and you come across a problem and you see, well, there's no moles mentioned and there's no temperature mentioned, you pretty much just scratch those guys out, and now you have Boyle's law right there. If you take this guy here, and you see no pressure or moles mentioned, you scratch those guys out, and now you have Charles' law. You can do it for, again, all those ones that we saw earlier. And just really all you have to do is scratch out the thing that's either being held constant or is not mentioned at all. So if you had no volume or moles mentioned, you scratch out the volumes, you scratch out the moles, and now you have Guy-Lussac's law right there. You can even get to Avogadro's law doing it that way as well. And that's at constant pressure and temperature. So you just scratch those guys out. And now you have Avogadro's law. So if you just remember those two, and pretty much anything that's being held constant, anything that's not mentioned in the problem, you just scratch it out and you'll have the correct gas law that you need to use. And that's a good way to remember all those gas laws without maybe having to remember them individually. You could just remember basically the ideal gas law, which is an important one, and this sort of version of the combined gas law. And you pretty much could get every gas law that you would ever need to use just by scratching out what's not there. Any questions on how to do that there? All right. All right, so let's try one here. Consider a sample of oxygen gas at 27 degrees Celsius at 9.55 liters and 297 atmospheres. We're going to change the pressure to 8.25 and heat it up to 125. We're looking at what the new volume here would be. So take a couple minutes there and see what you come up with. Okay, let's take a look. So once again, we're going to pull out the information. We got a temperature that's 27 degrees Celsius. We also have a volume 9.55 liters and a pressure that is 2.97 atmospheres. We got another pressure here, 8.25. We have a volume that we're looking for and another temperature of 125 degrees Celsius. So just looking at that, you should hopefully see sort of the combined gas law there. We'll call everybody there first ones, call these guys twos. By the way, or which ones you call ones and twos, as long as you keep the information together and put it on the same side, be equal. In this case, our atmospheres are good on both of them, which means we still need to do our conversion here. So we're going to add a 273 to each of these guys here. That's going to give us a 300 Kelvin and a 398. So at this point here, P1 V1 T1 equals P2 V2 T2. And in this particular case, we are looking for V2. That means T2 needs to go to the other side, so we'll end up on top when we multiply it, and P2 will end up on the bottom when we divide it. And a reminder, I think we talked about it last time, but if you do have the equal sign, quick way to rearrange is anything up here on top ends up on the bottom and vice versa. And as you go across the equal sign, everybody ends up in the opposite location. So if you do that, that will give you P1 V1 T2 divided by T1 P2 is equal to V2, which is on top by itself, which is what we're solving for. So putting in our numbers in the proper spots there, P1 being 2.97 atmospheres, V1 being 9.55 liters, and it is T2 that should go up on top, 398, divided by our T1, which is 300, and our P2, which is 825 atmospheres. Atmospheres cancel, Kelvin cancel, leaves us with liters as our unit that is left at this point. That gives us a 398 times 9.55 times 2.97 divided by 300 and divided by 8.25. Going to give us a 4.56 in terms of our liters in this particular case. Any questions on that one there? Yeah. You don't on this one. Yeah, if you just want to plug in the numbers, you need to show some type of work. So if you want to plug them in on both sides and however you want to do it at that point, it's fine. Yeah. Other questions on that? I will say this is the one that gives a lot of people very much difficulties in the rearranging part. So it's very common people sort of invert, like the T1 for the T2 and all that kind of stuff. So if it is problematic for you, again, the quick way is just to move it to the opposite location and take some time to make sure you know how to rearrange the equations because it's a very common sort of issue a lot of people have. All right, so continuing on. The next thing we're going to actually talk about is stoichiometry that involves gases. And gas stoichiometry, the good news is it's really the same sort of steps that we use in a really basic stoichiometry problem in a lot of cases. And those 4 steps, again, as we talked about, was to balance the equation. We want to convert to moles. We want to do the mole to mole relationship like we normally do from the balanced equation. And then we want to convert the moles to some other unit. Now, in addition, you can have and I would probably say in most cases, if you're doing some type of gas stoichiometry problem, it's probably going to be a basic stoichiometry problem. But you could, just to remind you, just like a normal stoichiometry problem, you could have a limiting reagent situation that could occur as well. So you obviously would do the same sort of steps that we did before to figure out the limiting reagent, but probably 9 times out of 10 is going to probably be just more of a basic stoichiometry problem where you don't really have to worry about the limiting reagent. But just to be careful, you can have obviously a limiting reagent problem as well. Now, the main 2 places where the difference comes when we do sort of a gas stoichiometry problem, one place where you might be a little bit different is in step number 2, and that is we will use the ideal gas law somewhere along the way in this journey. So we might even use it twice, but in most cases you'll use it once. And if you use the ideal gas law up front, you most likely would be solving for moles, like N is equal to PV over RT, like the second experiment you did last week, or you actually need to start with this to actually calculate the moles. So instead of doing grams to moles using the molar mass, we would use the ideal gas law, get the moles, and then you would actually proceed just like the normal stoichiometry problem. Most commonly, though, is in step number 4 here. We use the ideal gas law and we solve for something like volume, which is nRT over P. So these are 2 sort of common places where the ideal gas law gets inserted. Frankly, there are some problems where you could use them both together. But in most cases, I would say you probably use it at the back end. Everything else in the middle is sort of just a regular stoichiometry part, but somewhere there, either at the end or at the beginning or both, you have to use the ideal gas law. Any questions on that there? All right, so why don't you try one here and see what you come up with. We're looking for what is the volume hydrogen gas at 27 degrees Celsius and 1.25 atmospheres that reacts with 5.65 grams of phosphorus. I think you might have a typo on yours. That should be a 3 there. I think yours might say 2. That should be a 3 right there. And phosphorus from the periodic table is 3097. So take a couple minutes, follow those 4 steps for stoichiometry. Think about where you might need to use the ideal gas law here and see what you come up with, and then we'll talk about it there. Okay, let's see how you're progressing. So again, it is a stoichiometry problem. So our first step is done for us. We do have a balanced equation. We ultimately want to get to hydrogen gas here is really what we're looking for. We're really looking for a volume of hydrogen gas. We do have a temperature given to us of 27 degrees Celsius. We also have a pressure of 1.25 atmospheres. So a reminder that we will need to use probably the ideal gas law somewhere around here. And if we think about it to solve for the volume here of hydrogen gas, we do have the pressure given to us. We do have the temperature. We always have R given to us, which is not always given to us, but we always have it available. So we could see that in terms of what's sort of preventing us from solving the ideal gas law here is the moles of hydrogen gas. That's really where the stoichiometry part of it comes into play. We can actually use the last piece of information given to us, which is the grams of phosphorus, and go through our regular stoichiometry steps to get to moles of hydrogen that will allow us to eventually really do the fourth step here and use the ideal gas law. So that's really where we want to start. We want to start with our grams of phosphorus, and we want to convert it into moles from the periodic table. So that would be 4 times 3097 grams per mole of P4. At this point, the grams of P4 would cancel, and I would be in units of moles of it. But remember that we really don't want phosphorus. We need to get to hydrogen. So that's the stoichiometry comes into play. You could get a number at this point, or you could continue on and really do step number 3 here, which is the mole-to-mole relationship. So we can see from the equation, for every 1 mole of P4, I get 6 moles of H2. So 6 moles of H2 gives me 1 mole of P4. The moles of P4 will cancel, and that will get me 5.65 times 6 divided by 4 times 3097, 0.274. So really what I just did was the first 3 steps of stoichiometry, balanced equation, convert to moles, and did our mole-to-mole relationship, just like a normal stoichiometry sort of event. The purpose of that is really for number 4 here. So here we're going to use the ideal gas law here on the back end of the calculation. So once again, PV is equal to nRT. We now have our temperature, our R, our N, and our pressure. We just need to make sure everybody's in the right units. So we do need to convert our temperature there into Kelvin, and everybody else should be in the right units. We now can solve for the volume of hydrogen gas would equal nRT divided by P. Putting in our moles we just calculated above, 0.274, our gas constant, and our temperature that's been converted to Kelvin, all divided by our pressure, which was already in atmosphere, so we were good on that. The moles will cancel, Kelvin will cancel, atmospheres will cancel, going to leave us liters as the only unit that's left, and that would get us 0.274 times 0.0826. Looks like 5.40 liters of H2 in this case. So this would be really step number 4. And again, in sort of gas stoichiometry, instead of using molar mass at the end, here we're actually just putting it into a gas law, the ideal gas law here at the end. But it's really the same sort of 4 basic steps there that we've done in a regular stoichiometry problem. Any questions? Okay, let's try another one here to make sure this is pretty much identical to what you did in the first experiment last week, this equation here. So calculate the volume of hydrogen gas that's produced at STP if you started with 5 grams of magnesium via this reaction. Okay, let's take a look. So once again, a reminder that STP, it does represent 2 values. The temperature is 273 Kelvin, and the pressure here is basically 1 atmosphere. So in this particular case, we can do our stoichiometry. We do have our temperature or pressure. We are ultimately looking for H2, but we are starting with magnesium. So after our balanced equation there, the first thing we would want to do is convert it into moles of magnesium, 2431 grams per mole of magnesium. Again, much like the previous problem, if we use the ideal gas law here, we have temperature, we have pressure, we have R, we are looking for volume. So once again, we do need to get to moles of hydrogen gas, which is really where the stoichiometry part comes from. In this particular case, it is a 1-to-1 relationship between those two, which makes the math not too bad there. So that's going to be 1 mole of magnesium, 1 mole of H2. Moles of magnesium cancel, so does the grams. And at this point, we would end up with 5 divided by 2431 gets us 0.206, I think, moles. In this case, this would be step 1, step 2, and then obviously our step 3 here, converting to the moles what we're looking at. That also then gives us the sort of missing piece that we would need for the ideal gas law. We could take the ideal gas law here and solve for V, which would be nRT divided by P. This gives us moles of 0.206, our gas constant, our temperature, which would be 273, all divided by our pressure, which is 1 atmosphere. Atmospheres cancel, moles cancel, Kelvin cancel, leaves us liters, gets us 0.206 times 0.08206 times a 273, about a 4.61 liters there of hydrogen gas would be produced at STP. First off, any questions on that calculation there? Now, because this was at STP, we could have also took an alternative approach. Because of this STP, we know that at STP, 1 mole of any gas equals 22.414 liters. What that means is essentially, taking it from this point here, when we get the moles of the hydrogen, we could use that conversion in this case. The moles of hydrogen would cancel, and you'll end up with the exact same answer, actually 4.62, a little bit with rounding, but pretty much the same answer as you go that way. So this is a case where you could use that conversion factor and not have to use the ideal gas law, which could save you some time. A reminder that you can only use that conversion factor if it is at STP. So again, if it's not at STP, you can always use the ideal gas law for any situation. You just put the numbers in like we did above. Any questions on that there? Okay. So then let's talk about let's talk about one more sort of stoichiometry sort of situation. Let's say we had an equation like this: 3 hydrogens plus N2 gives us 2 NH3. All right, now let's just say that we started with 5 liters of H2, and we wanted to know how many liters of NH3 would we produce at, we'll just do a temperature of 295 Kelvin and like a 1.35 atmospheres. So this is a situation in a stoichiometry problem where you technically could use the ideal gas law in sort of 2 situations, at the beginning of it and at the end of it. So for example, we obviously have all the information here. If we look at the ideal gas law, say for hydrogen, we know the pressure, we know the temperature, we know R, and we have the volume of it. That would allow us to actually solve for the moles of hydrogen at the beginning. So this would be a situation where you would actually use the ideal gas law up front and solve for N. So we have a balanced equation. We then would do the second step, which is actually solving for moles by using the ideal gas law up front here to actually solve for the moles. And these would be moles of hydrogen. And in this case, we have the pressure, which would be 1.35 atmospheres. We have the volume, which is 5 liters of hydrogen divided by our R. And our temperature, which would be, what did I say there, 295, I think I did. And that's going to give us 1.35 times 5 divided by 0.08206 divided by 295. That'll give us approximately 0.279 moles of hydrogen. In this case, we are looking for NH3. So if we think about the ideal gas law here for NH3, we have the same pressure, we're assuming. We have the same temperature, we have R, and we are looking for the volume, which once again means we are going to use stoichiometry to figure out the moles of NH3, which is what we're missing. So we would do our third step here with stoichiometry, which would be going from moles of hydrogen to moles of NH3. So from the equation, 3 moles of hydrogen gives us 2 moles of NH3. And that gets us 0.279 times 2 divided by 3, 0.186 moles of NH3. That means we now have the moles of NH3 to use our ideal gas law here one more time. But in this case, we would solve for volume. And again, we're bringing pressure to the other side in this case. Putting our numbers in here, we end up with our moles of our NH3, which is that. Our R, 0.08206. And our temperature, 295, all divided by 1.35 atmospheres. Everything cancels out except for liters, which leaves us our volume that we're looking for. And in this particular case, we end up with about 3.34 liters of NH3. So this is a stoichiometry problem involving gases where you could use the ideal gas law not once, but actually twice. And that is usually what would happen if you did that. You would use the ideal gas law to solve for moles early on and then probably volume at the end. Now, you could definitely do it just like we just did there. But we could also use, in this situation, since really in this problem, the pressure and the temperature was actually held constant, right? It was the same pressure and temperature all the way through for each gas. Nothing really changed in terms of the pressure and temperature. So when we have constant temperature and pressure, that is where we have Avogadro's relationship there, or Avogadro's law. And one of the aspects of Avogadro's law is when you have constant temperature and pressure, you could look at stoichiometry like in this equation and do a mole to mole relationship like we did. But because the moles and the volume are pretty much the same in that situation, you could actually just directly do a volume to volume relationship between the two. And you could say, just like you would do with stoichiometry and the coefficient, 3 liters of H2 gives us 2 liters of NH3. And you could do it for anybody in the equation. You could also say, for example, 3 liters of H2 gives us 1 liter of N2. And just like you could do a mole to mole relationship, you could actually do a volume to volume relationship. Because of this situation, they're gases and it's a constant pressure and temperature. Why that would be advantage here is we literally could in this problem go, I got 5 liters of H2. I could go to the equation, do my volume to volume relationship, where it shows us that there are 3 liters of H2 for every 2 liters of NH3. And when you take basically 5 times 2 divided by 3, you get basically 3.33 liters without having to use the ideal gas law in either spot. So this is a very useful relationship, and it does come from Avogadro's relationship. that if you happen to be doing a stoichiometry problem where you're given the volume, the pressure and temperature is held constant, and you're asked for the volume of somebody else in there, and it's constant pressure and temperature, you could just do a volume to volume relationship and not have to worry about a gas law at all, and just do a stoichiometry problem just like that. Any questions on that? So very similar to where you can only use the 1 mole is equal to 22.414 liters for SCP. You can only do this if it's gases and constant temperature and pressure. If you can't remember that, you can still, as you see there above, do the ideal gas law in both places, and you'll get the same answer, obviously, with rounding pretty close. Any questions on that there? Questions on gas stoichiometry? And again, a reminder, as I mentioned earlier, that you could have a limiting reagent type situation, and you would do the same sort of steps that we did previously to figure that out in the gas law. I would say probably most of the time it's not going to be a limiting reagent situation, but you could potentially have something like that. Yeah. Yeah.
How would you know to do it twice?
So it would be kind of like the problem like we had there where basically we have gases and gases. So in this situation, we pretty much had information about a gas, and then we were looking for a gas, and there was really no grams or anything like that to get the moles of that first guy. So all we had was sort of the gas information to allow us to get there. So that's how you got to know you could use the ideal gas law on the front of that. So there's no way for that hydrogen in this case other than doing it that way. Yep. Excuse me. Other questions? Okay, so next thing we're going to talk about is Dalton's law of partial pressures. And it sounds really difficult, but it's a pretty straightforward concept. The idea here is if we had a container that only had excuse me, one gas molecule in there, one type of gas molecule like A, the only person contributing to the pressure here of this container is gas molecule A. If we have a container where there are multiple types of gas molecules, say A, B, and C, as they are all flying around, they're all basically contributing to the overall pressure in that container, which means the total pressure here would be the result of the pressure of gas molecule A, the pressure of gas molecule B, and the pressure of gas molecule C. Those are referred to as partial pressures because they each contribute partially to the overall pressure of the mixture. So to find really the overall pressure, which by the way is in a experimental situation, the atmospheric pressure, like when you read the barometer in class, that would be the total pressure. To find that, we basically just add up all the partial pressures together. How do we find the partial pressures of each of these gases? In most cases, it is our good friend here, the ideal gas law, which is PV equals nRT. And basically, because this is an ideal situation, even though there are multiple gases in there, we basically could just solve for P for each gas individually. And we just assume that they're not interacting with each other. And that's really the idea of an ideal gas, is even though they're in there, they will not be pretty much interact at all with them. The nice thing about sort of doing this and solving it that way is because they are a mixture of gases, the temperature for all the gases would be the same because they're in the same container. The volume for all the gases would be the same. So if you think about the ideal gas law, temperature is the same for everybody, volume is the same, R is a constant. Really, the only difference that you have is basically you just need to find the moles of each of the individual gases. And that's the only thing that would be different in the calculation for each of them. You would do just in this case, for example, if we had two gases, two separate ideal gas law calculations, that would give you the partial pressures of each of the gases. and then you basically just add them together and you would have your total pressure at that point. Any questions on that there? All right. We'll come back to this guy in a second. So why don't we try one here? We have 5 grams of helium and 5 grams of neon. It's at 2.5 liters and 27 degrees Celsius. What is the partial pressures of each gas and the total pressures? Neon is 2018 and helium is 4.003. So we're looking for really 3 answers here: the partial pressure of helium, partial pressure of neon, and the total pressure of the mixture. Take a few minutes to see what you come up with here. Okay, so let's see how we're doing. In this situation, we have helium and we have neon both flying around the same container. Again, in an ideal situation, even though they're in the same container, it doesn't really matter. We could just think of them as being in there by themselves. But what is the same for both of them? Again, they both have a volume of 2.5 liters. They both are at a temperature of 27 degrees Celsius, which would become 300 Kelvin if we convert it to Kelvin. So in this case, we are going to really use the ideal gas law for each of them individually. We have the temperature, we have R, and we have the volume. We do need to get the moles of each of these guys. So to start with here, we have 5 grams of helium using the molar mass from the periodic table, 4.003 grams per mole. We also have 5 grams of neon using its molar mass from the periodic table, and we'll convert that to moles as well. That will get us 5 divided by 4.003, 1.25, we'll call it. And 5 divided by 220.18, 0.248. And really, in this case, we're just going to do 2 separate calculations. So we'll start with the partial pressure of helium, which would be nRT divided by V, really just bringing V to the other side. And we'll put our values in for helium, which is 1.25 moles. And our gas constant and our temperature, which was 300 Kelvin, all divided by our pressure there. I'm sorry, our volume, which is 2.50 liters. That gives us 1.25 times 0.08206 times 300 divided by 2.5. Gets us about a 12.3 atmospheres as the partial pressure of helium in this case. We're basically going to do the exact same calculation for neon. The only difference is the moles. So we want to make sure we put in the moles of our neon in this case, which would be 0.248 moles. Our R, our temperature, and once again divided by our volume, 2.5 liters. And if we do that, 0.248 times 0.08206 times 300 divided by 2.5 gets us a 2.44 atmospheres. That would be the partial pressure of neon in this case. Any question on either of those calculations? So to find the total pressure, all it has to do is just add those 2 together, basically. So the total pressure in this case would be the partial pressure of helium plus the partial pressure of neon, which would be 12.3 plus 2.44 atmospheres. And that would get us 14.7 atmospheres here would be our total pressure. Any questions on that one here? Major contributor to the pressure in this case is which gas? It is helium, and the reason for that is helium is much lighter, yeah? So it's lighter, which means it will be flying around, have a much higher velocity. So it'll be banging around a lot more than the slower moving, heavier neon would in this particular case. Any questions on that there? All right, another sort of partial pressure situation like the one that you had in your labs last week is a situation like this. I think this is the exact lab we did. So in the last lab that you had some potassium chlorate. When you would heat that, it went through a decomposition reaction and generated some oxygen. Oxygen had nowhere to go, right? But to your container, which originally started with water in it, right? And as the gas came in, it basically displaced the water. So in that empty spot, you had your oxygen gas. But as a consequence of how the gas was collected in this experiment, and also the first experiment where you took the tube and you put it in a giant beaker of water, right? Was we also had water vapor that would come along for the ride here. And that is because as the reaction would happen, it would heat up some water, you'd collect some water vapor in there. So what you actually had here is actually a partial pressure situation. The total pressure is equal to the pressure of the gas you're interested in, plus the vapor pressure of water, which is what that is sometimes referred to. As you may remember, as you did last week, that is usually a table value that you could look up in a table based off of temperature, which was hanging on the board, I think, in lab. And the reason you would want to do that is when you do an experiment like the one we did there on Wednesday and the one you did on Monday, you're not really interested in, say, the pressure associated with the water vapor and the hydrogen, or the water vapor and the oxygen. You're really interested in just the pressure associated from the gas that you collected. So we have to do sort of a correction for that water vapor, and it ends up being the pressure of the gas you're interested in is the total pressure minus the vapor pressure of water. The total pressure, again, from a laboratory situation would be the barometer reading, atmospheric pressure in that case. So in this case, if we wanted just the pressure of the oxygen gas, it would be the total pressure minus the vapor pressure of water. This is also sometimes referred to as the dry gas, yeah, or to get the pressure of the dry gas, because you're subtracting off the contribution of water. It is really just sort of an artifact of how the gas was collected rather than being produced as a result of the reaction you're looking at. The reaction you're looking at doesn't produce water vapor. It's just, again, a byproduct of how you collected it. So when you do your calculations for these type of problems, when you do these type of experiments, you really want the pressure just associated with the gas you're collecting. And that should be the pressure that you use when you do any of those type of calculations. You should always use the pressure of the dry gas where you subtracted off the water vapor's pressure. So this would be a problem where this situation would occur. A sample of oxygen gas is saturated with water vapor. That's like a key in a textbook problem. It says something like saturated with water vapor, collected over water. Some mention of water tells you that you are in that situation we were just talking about, that the total pressure is the pressure of the gas plus the vapor pressure of water. In this case, they do give us the total pressure, which was 753 torr, is equal to the pressure of oxygen gas. And they were nice enough to give us the table value here for the vapor pressure of water. If it wasn't given to you, you would have to go look it up, obviously, on the table. And in this case, we could very easily solve for the partial pressure or the pressure of oxygen gas by taking 753 minus 31.824 torr in this particular problem. And that gives us 753 minus 31.824, about 721 torr. That would represent the pressure of the oxygen gas by itself without the water vapor. And again, we did want atmospheres here, so we would divide by 760 to convert it into atmospheres. And if we did that, we would end up with 0.949 atmospheres. And that would be the pressure of the oxygen gas in this case, without the contribution of water, obviously. And if you were going to continue on and needed the pressure of oxygen in a calculation, that would be the value that you should use, not the one that still has the water associated with